Mr. Tarou. All right. So in today's lesson, we're going to be taking a look at sequences, being reminded of what those were in pre-calculus. Coming up, we're going to be reminded what recursion formulas are in a general nth term. We're going to be graphing some sequences and possibly, if we can, a function over that and see the relationship between how the plot of sequences, the general term a sub n terms, varies from plotting an actual function, which has a different, less restrictive domain. We're going to be writing out the extending some and finding more additional terms of given sequences and then writing a general term for those, determining the convergence or divergence of a sequence to build up a little bit of understanding of what it means for something to converge so that we can move into determining some convergence and divergence of series through the rest of the chapter. So a sequence is a function whose domain is the set of positive integers. Now, when we were studying these for the first time, or reviewing them actually we were reviewing them for the first time in pre-calc, but you should have seen them for the second time. When we looked at these in pre-calc, we had two types of settings for creating terms in a sequence. We had a set of recursion formulas where we have two equations that are going to tell us how to build out a list of numbers. And recursive or recursion formulas are very easy to come up with. They're also really useful if you're using technology like programming to model real-life situations like the burning of solid fuel in rockets. If you're like an aeronautical engineer and you have really powerful computers that can crunch numbers very, very quickly. We don't really like recursion formulas too much in our classrooms and in class because we're going to be doing a lot of math without the aid of calculators, and there's a major problem with working with recursion formulas. They're easy to come up with, but they're monotonous to work with. So we're going to have a list of numbers where n is equal to 1 and 2 and 3 and so on, which means we're going to be coming up with an a sub 1 and a sub 2 and a sub 3 and a sub 4 and so on, using this set of recursion formulas. What's a sub n if n is equal to 1? Well, when you have recursion formulas, you have to be given something to start with. So our first term in the sequence is going to be 3. So a sub 1 is going to be 3. When n is 2, I'm looking for a sub 2. So a sub 2 is going to be equal to 2 times a sub 2 minus 1, or a sub 1 plus 1. So we're doing 2 times the previous term plus 1. So what's 2 times 3? Plus 1 is 7. How about a sub 3? That's going to be 2 times a sub 2, because 3 minus 1 is 2, plus 1. So 2 times the previous term, a sub 2 is 7, plus 1 is 15, and what's our next number going to be? 2 times 15 is 30, plus 1 is 31. Okay, now that means that the only way that I can find, and I wrote n equals down here, but I'm going to write this a little bit differently as a sub 1, a sub 2, a sub 3, a sub 4. The only way that you can get to the fifth term in the sequence when you're using a set of recursion formulas is to build out the first 4. So yes, we've already got the first 4 terms. So to say that a sub 5 is going to be what? 2 times 31 is 62, plus 1 is 63. That was only a quick process because we already had the previous 4 numbers. Whereas if we have a general term, if you want a sub 5 for this general term, which is a sub n is equal to 2 to the nth power over n factorial. Maybe we'll do a sub 4 so the numbers aren't so big. If we want a sub 4, that's going to be 2 to the 4th power over 4 factorial. Well, I can just jump to this 4th term and calculate it. I don't have to find a sub 1, a sub 2, and a sub 3. So 2 to the 4th is what? 2, 4, 8. 2, 4, 8, 16. And who remembers how factorials work? What's 4 factorial?
24.
Well, that was quick. How do you find that answer? 4 times 3 times 2 times 1. And we can multiply all that out. 4 times 3 is 12 times 2 is 24. Or since we have a division of some constants, basically, 4 times 2 is 8. And 16 divided by 8 is 2. So our final answer is going to be 2/3. And here we have a sub 4 is equal to 2/3. We got to that 4th term in the sequence without having to find the first 3. So in our math classes, in this chapter, we're going to be really focused on that general term of a sequence and not working with a set of recursion formulas. I just wanted to remind you of that. Okay, let's take a look at what the graph of a sequence looks like. So we got a sub n is equal to 21 over n plus 2. So remember that the domain of sequences are only positive integers. So I got a little t-table set up here, and it looks like any t-table that we would do in the early parts of algebra when we were graphing functions and we didn't know what they looked like. We would just, make a t-table. So when we do n is 1, we got 21 over 1 plus 2, which of course is 21 divided by 3, which is 7. And then we've got 21 when n is 2, we got 21 divided by 2 plus 2, which is 4. So 21 divided by 4, right off the top of my head, is 5.25. We got 21 over, when n is 3, 3 plus 2 is 5, and 21 divided by 5 is 4.2, and then so on and so on. We have 3.5 when n is 4, and we have 3 when n is 5. When we go to plot the graph of this sequence, we've got the coordinate of 1, 7, 2, 5 1/4. This is just a sketch, obviously. We've got 3 and 4.2, 4 and 3.5, and then 5. When we got 5, we're down to 3. And resist the urge to lay down, sort of a graph on top of these coordinates, because that is the graph. The domain of sequences is what? The domain of sequences are positive integers. So the graph of a sequence is not continuous. That's going to be important to problems that we do through the rest of this chapter when we're determining if a sequence is convergence or not. And we're doing different tests like a p-series test, a telescoping test, a root test, a ratio test, a limit comparison test, especially an integral test for convergence coming up in a couple of sections. This is the graph of the sequence a sub n is equal to 21 over n plus 2. But there will be times where maybe we want to not just work with the sequence notation, but it might be at times convenient in this chapter to work with a function that basically acts very similar to the sequence general term. So we can say let f of x be 21 over x plus 2. And this is going to be great if for, first of all, it actually acts as a proper function. And when x is an integer, we get the same answer that we get from the sequence. And indeed, if we graph f of x is equal to 21 over x plus 2, we get this function, which is going to be useful later on in this chapter. F of x needs to be a proper function that works. It has a domain of, in this case, all x greater than or equal to 1. It actually has a domain of x is greater than 0. But if we're using a function to help us determine interesting characteristics of sequences and series through the whole chapter, we're really only going to be actually going to care about the domain of this being continuous and being greater than or equal to some initial positive integer. And we do have a case here where f of x is equal to a sub n when x is a positive integer. Now I'm bringing this up as something that kind of seems important when you might think it seems obvious for questions like we have this second example here. We have a sub n is equal to negative 1 to the n power over n. We're going to see that this is later on called an alternating harmonic series. And we're going to have harmonic series that we talked about in pre-calc as well that we're going to revisit. If n is equal to 1, we have negative 1 to the first, which is negative 1 over 1, which is going to be negative 1. When we let n equal 2, we're going to have negative 1 squared, which is positive 1 over 2. So we have a positive 1/2. If we let n equal 3, we're going to have negative 1 cubed, which is negative 1 over 3, or negative 1/3. And then when n is 4, we have 1/4. And when n is 5, we have negative 1/5. And when we plot this, we're going to have 1, negative 1. We're going to have 2 and 1/2, 3 and negative 1/3, 4 and 1/4. That should be a little bit closer to the x-axis there. And then we have negative 1/5. Okay, would it make sense in this case, would it work for us to say that we're going to graph on top of this graph of the sequence, a sub n is negative 1 over n to the n power? Would it make sense for us to say, let f of x equal negative 1 to the x power over x? Could we actually graph that and use a function to act like the sequence? Why not?
Because the sign continuously flips.
The sign continually flips. That's a true statement. But wouldn't this graph then just oscillate and make like a smooth oscillating curve between these, almost like a sine of x over x? Can you give me if I were to make a t-table with this, could you give me a value that for this, that the function would not work? Because functions have domains, functions have a domain that's continuous to some, I mean, of course, this function would be undefined when x is equal to negative 2, right? If you were to graph this function, f of x is 21 over x minus 2, you would have a graph with a vertical asymptote at negative 2. So it's not correct for me to say that the domain of functions are like all real numbers. There can be restrictions. But if we want a function to act and be useful, like if we want a function to sort of like act and work with a general term of a sequence, that function has to have a domain that's continuous after some initial value, which is a positive integer. And so here we have a sub n is negative 1 over n, negative 1 to the nth power over n. And I made a t-table starting when n is equal to 1, a positive integer. And we got a graph. Can we come up with a number that's greater than 1 for which this function would not work? 3/2. And what's wrong with 3/2? If we do f of 3/2, we're going to have negative 1 to the 3/2 power over 3/2. Well, what's the denominator of a fractional exponent? It's a square root. And can you do square root of a negative number? I mean, you can if you're in the world of imaginary numbers. But if we're talking about a real x and y axis, that imaginary number is going to be a problem. So for this alternating harmonic series, we can graph the sequence, this will become an alternating harmonic series. But for this general term of negative 1 to the n over n, we can graph the sequence, but we cannot graph a function. We cannot create a function that really truly works as a function and agrees to the sequence expression for every value of x that's greater than or equal to 1. So that's going to come up, especially when we start talking about an integral test of convergence, when we get to, I think it's in 9.4. The limit of a sequence. If the limit of L of a sequence exists, and when we talked about limits in chapter 1, we were talking about real values. So a real finite, whether it be positive or negative, real finite value. So like, a real number like 4 or pi or 7, but not an answer of like infinity. So if the real limit of a sequence exists, then the sequence converges to that real value of L. If the limit of the sequence does not exist, so we're going to be finding limits of a sub n terms. If our limit of a sub n comes out to be either positive or negative infinity, we're going to say that there is no real limit, and that limit, and therefore the sequence is going to be said to diverge. So we're going to be doing some review of how to take limits of some expressions, maybe doing some algebraic simplification, maybe doing some L'Hopital's and such. But before we do that, I want to take a look at some examples, and we're going to need, for some of the problems in our homework, to come up with a general term for a given list of numbers. Okay, it's just we're not adding these numbers, we're not multiplying these numbers, we're just listing them out. And we've got this list of numbers of 3 over 2 for our first example. We're going to write the next two terms of a given expanded sequence. And we're going to find the general term, the nth term. When I say the nth term of a sequence and the general term, I'm kind of saying the same thing of that sequence. So we have 3 halves, 2, 5 halves, and 3, and then a couple of unknowns. If n is equal to, or if this first term is a sub 1, and the next term is a sub 2, and a sub 3, and a sub 4, what is a sub 5 and a sub 6? How do you turn the domain is the positive integer. The domain is really, you see this a sub n, the n is your independent variable in your general term. So how do you turn a 1 into 3 halves, a 2 into 2, a 3 into 5 halves, a 4 into 4? Try that out for a second. All right, so what'd you do?
I took the first initial number, and then I recognized that it was just adding by 1 half.
Okay, so then how did you use that to get your final answer?
So I started with the first number, 3 over 2, and then I added something over 2, because I know it's going to be by 1.
So like a x over 2?
So I did
Like
n minus 1 over 2. Because, for example, if I'm looking for the second number, I want this.
Okay, how did you come up with the idea that you had your initial term of 3 over 2, n minus 1 over 2. Where'd you get the n minus 1 from?
So if I want the second number, I need to be, the initial number has to be added by 1 half. So if I want the second number, I have 2. So I have to subtract by 1 to make it 1. Is that kind of,
I like, okay, I mean, it works. I like it. You're using the addition of 1 half. It's just, that's a pretty, and you are really good at thinking mathematically, a pretty abstract way of coming up with that n minus 1. Did anyone do anything different? Here's my suggestion, even though that was what you said was beautiful. If you start seeing fractions in your sequence, you should make everything look like a fraction and create some commonality or obvious pattern in either the numerator or denominator. It doesn't need to be both, but like create and focus on just one part of the fraction. So when I have the 3 over 2 and the 2 over 1 and the 5 over 2 and the 3 over 1, I'm seeing that if that's 3 over 2, then this is going to be a 2 over 1. And then a 5 over 2 and a 3 over 1. Okay, so now that every one of my first 4 terms is a fraction, let's make some like really obvious similarity, whether it's exactly equal denominators or a really easy to recognize pattern in the denominators or numerators. If I have some denominators of 2, I can very easily make these green denominators of 1 into denominators of 2. So I'm going to multiply 2 over 1 by 2 over 2, like basically find common denominators, like I'm going to add these fractions. And we're going to get, my first term is 3 over 2, and then a sub 2 is still going to have a value of 2, but I'm going to write that as 4 over 2. And then 5 over 2, which was the given third term, and then a sub 4, if I want to make that common denominator of 2, top and bottom by, multiply by a factor of 2, and we get 6 over 2, and so on and so on. Now that we've made the denominators all equal, every single one of these first 4 terms has the same denominator. So the general term, I'm pretty confident, is going to have a denominator not of n, but a denominator of 2. And now that we have the denominator set to an easy pattern, or in this case a constant, look at the numerator. For the first term, n is 1, and our numerator is 3. Then for the second term, our n is 2, and the denominator is 4. For the third term, we have 5. For the fourth term, we have 6. How's 3, 4, 5, and 6 compared to the n value of 1, 2, 3, and 4? They're all 2 larger. So we have n plus 2. Now, whether you come up with the general term first before you extend the list of numbers, or you extend the list of numbers first and then come up with the general term, I don't really care. But obviously, just because I've written a sub n is n plus 2 over 2 doesn't mean it's right. You better go back and like, okay, let's let n equal 1. We got 1 plus 2 over 2. Yep, that's 3 over 2. Let's let n equal 2. We have 2 plus 2 is 4 divided by 2, which is 2. And double check your arithmetic, double check your, what you believe the general term to be. And once it starts working out that it's good, then either, move on to the next problem, or in this case, use that general term to write your next 2. So when n is 5, what do we have? 7 halves. And when n is 6, what do we have? 4. Perfect. So take that example and try and come up with the general term of a sub n. What do you see in the third, fourth, fifth, and sixth term? You see a fraction. So let's make everything look like a fraction. So let's put this as 1 over 1 and negative 3 over 1. Do you see a easy pattern to recognize in either the numerator or denominator? It may not be complete through the whole list of all 6 numbers, but something seems to be standing out that's happening. Okay, so they're alternating signs. So our a sub n is going to have some form of negative 1 to some kind of power. We'll make that like an n or n plus 1. We'll adjust if needed. Or actually, let's just go ahead and do that now. Let's remember that this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and a sub 6. This first number is positive. And if we have negative 1 to a positive 1, is that going to be positive or negative? Our first term is positive when n is 1. So if I let n be 1, what's negative 1 to the first? That's negative, but this first term is positive. So we need to adjust this a little bit. It's not going to be negative 1 to the n. It's going to be negative 1 to either n plus 1 or minus 1. It doesn't make any difference which one you use. So I'm going to use plus 1. Okay, so it's alternating. What else do you see in the numerator that seems like it's a pattern that is developing? We're multiplying by 3. Okay, so let's make sure that's true for all of these terms. So that means we've got 1 over 1, negative 3 over 1, multiply negative 3 by negative 3, or, well, we've already got the alternating part taken care of. So doing 3 times 3, we get 9 over 2. But you noticed a multiplication of 3. So This is 9, and we have 9 again. So let's take 1 times 3, 3 times 3, 9 times 3, which is 27. Why are you giving her the answer like she can't do arithmetic? So we just did 9 times 3 to get 27. So if we multiply the numerator by 3, we have to multiply the denominator by 3. So it's going to be 27 over 6. Of course, it's got to be negative because it's there negative in the first place. Okay, now we got another little bit of a problem here, right? Because if we do 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, our next term has a numerator of 27. So having 27 over 8 is kind of breaking this potential pattern, which might not be, it might not be the pattern. I mean, we got to get to the 243 and make sure that it actually works. So we got times 3 times 3 times 3. Let's see if we can't multiply by 3 again. What is 27? What's 27 times 3? 81. So we have 81. If we multiply the numerator of this fifth term by 3, we have to multiply the denominator by 3. So we get 24. Now, let's hope that we can multiply the numerator by 3 again and get 243. What's 80 times 3? 240. But then it's 81, so we have another 1 times 3, which is 23. So positive, negative, positive, negative, positive, negative, and multiplying by 3, 81 times 3, thankfully, is coming out to be 243. So nice job on recognizing that potential multiple of 3. And we have our denominator of 120. So thanks to Anna, we're turning 1 into 1, 2 into 3, 3 into 9, 4 into 27, and so on by some kind of, if we're repetitively multiplying by 3, repeatedly multiplying by 3 is what? If you repeatedly multiply by the same number, that is a power. So it's going to be 3. Now it's 3 to what? Is it 3 to the n? I don't think so, because 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. We seem to be like one behind, right? So it's not going to be 3 to the n. It's going to be 3 to the n minus 1. And since we have one exponent of n minus 1, I'm going to make this first exponent also n minus 1. Now, what is our denominator, though? Ooh, you guys got quiet. What's happening down here? Multiplying by 1. What's happening to get to the third term? You're multiplying by 2. And then you multiply by 3. And then you multiply by 4. And then we're multiplying by 5. So if you have a list of numbers that are created by multiplication where the multiple keeps going up by 1, what pattern is that? Factorial. So we have some kind of factorial in the denominator, but is it n factorial, n minus 1 factorial? Because first we multiply by 1, and then by 2, and then by 3, and then by 4. So if this is a factorial, this has to be some kind of n factorial down here. Well, if n is 2, 2 factorial is not 1. And if this is 3, 3 factorial is not 2. So these denominators are not, it is a factorial, but it's not n factorial. Yeah, and by the way, since we're talking about factorials and we haven't talked about these a long time, the definition of 0 factorial is 1. And then you have 1 factorial, and 2 factorial, and 3 factorial, and 4 factorial. So whatever n is, it's that number minus 1 factorial. So for b, our general term is basically negative 1 to the n minus 1 times 3 to the negative 1, or negative 3 to the n minus 1 power over n minus 1 factorial. And now that's the general term. And to create the next two numbers in this list, you just keep going, multiplying by 1, multiplying by 2, 3, 4, 5. Now what's 120 times 6? 720. And 720 times 7. Yeah, these numbers are getting really big. Actually, let's just go that. Let's not even worry about the next biggest number. We'll just cut that one off. And so our next term is going to be the net. What's 243 times 3?
729.
What is it? 729. All right. So there we go. We added one more term and came up with our general term of this. What is the limit as n approaches infinity of n plus 1 factorial over n? Do you remember how to expand factorials that we looked at in chapter, in pre-calc? What's a factorial do?
Multiplied by the
Your multiplication repetitively, and you count down by 1 until you get to 1. So the limit as n approaches infinity of n plus 1 factorial, what would that expansion look like? It's going to be n plus 1 times the previous integer, which will be n, times the integer before that, n minus 1, down to 3, 2, 1. Now, we don't know how many factors we're going to have, but we're going to start with that first factor of n plus 1 and subtract by 1 until we get down to 1. What is n factorial? N times, well, I don't know about the half part, but yeah, n factorial is n times n minus 1 times yada, 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 down to 1. So n plus 1 factorial over n factorial is going to reduce to just simply be n plus 1. So the limit as n approaches infinity of n plus 1 is what? It's infinity. And beyond. So because this is infinity, and I guess maybe arguably I should be giving you the initial sequence. Therefore, the sequence a sub n diverges. There is no limit to that. So for our second example, at least going right to left, for some reason I'm doing this, we have the limit as n approaches infinity. Is it okay? Yeah. Okay. We have the limit as n approaches infinity of negative 1 to the n over n. Now, when we get into the world of sequences and not when we get into the world of series instead of sequences, we're going to be calling this the alternating harmonic series. And we'll have a conversation about what it means when we do the alternating series test. We'll be talking about the difference between absolute and conditional convergence. I'm kind of giving you like a little bit of a hint as to what's coming up. If this were like, say, the limit as n approaches infinity of this, maybe, I don't know, sine of n over n, we might be doing a review of the squeeze theorem, which we do need to do, by the way. I'm just not going to have time today, to prove that the value of that ultimate limit. But we do have a statement here that says, for the sequence a sub n, if the limit as n approaches infinity of the absolute value of n is equal to 0, then the limit as n approaches infinity of a sub n is equal to 0. So we have a little negative 1 to an n power. So the list of numbers in this sequence is going to alternate between being positive and negative, and that may, you think, would add some complexity to the evaluation of this limit. And in certain circumstances, it might be. It might. But if a sub n is, well, negative 1 to the n power over n, I don't know why I'm doing extra parentheses here, then the absolute value of a sub n is just going to be 1 over n. And what's the limit as n approaches infinity of 1 over n? It's equal to 0. So we had an alternating a sub n term. We took the absolute value of it. We got 1 over n, and the limit as n approaches infinity of 1 over n is equal to 0. Therefore, the limit as n approaches infinity of negative 1 to the n power over n is also equal to 0. And for our third example, we have a sub n is equal to the natural log of n to the fifth over 3n. Now, if you look at this, we have the limit as n approaches infinity of the natural log of n to the fifth. And if you think about what the natural log function looks like, that's a graph that if I graph y is equal to the natural log of x, that graph, it almost looks like it's asymptotic, but we know the natural log function never stops increasing, then there is no asymptote. So the limit as n approaches infinity of the natural log of n to the fifth is going to be what? What's this numerator going to grow to? Infinity. And the limit as n approaches infinity of the denominator, which is 3n, is also going to be infinity. So for this sequence of a sub n is defined by a sub n, which is natural log of n to the fifth over 3n, the limit of the numerator and denominator individually as n goes to infinity is infinity. That is a form of indeterminate. So how are we supposed to analyze this limit? What did we learn fairly recently to analyze the limit of fractions that where the numerator and denominator both give an answer of 0 or some form of infinity? L'Hopital's rule, right? But L'Hopital's rule means that you're taking the derivative of the numerator and denominator separately. Well, what's the condition for taking a derivative? You need to have a continuous function. And what's the domain of sequences? Positive integers. They are not continuous. So to apply L'Hopital's to this sequence would not make any sense. You're kind of like skirting around, you're cheating that condition that's required for taking a derivative, which is the function is continuous. This is just a bunch of dots, not a continuous function. So here, if we let, whenever I say that there's a limit L, I'm talking about a real number. So if L is a real number, let f of x be a function of a real variable such that, basically we're going to create a function that acts exactly like our sequence expression, like where I overlaid that one function over the sequence a little bit ago. If the limit is, that's cute. If the limit, a lot of times I don't notice stuff like that when I'm teaching. The limit as x approaches infinity of f of x, if you can write that, if we have the limit as x approaches infinity of f of x is that real limit, okay, and the function f of n is equal to a sub n. Okay, notice this time, now this is not a typo, this is f of n. I'm saying that we're going to write a function f of x that needs to, for every positive integer, give the same answer as our general term of our sequence. So if f of n gives the same answer as a sub n, and f of x is a function of a real variable, after some positive integer, you basically have a domain that's all real numbers. If the limit as x approaches infinity of f of x is equal to L, then the limit as n approaches infinity of a sub n is equal to L. So we're going to use that to say we're going to be trying to figure out, again, the limit as n approaches infinity of the natural log of n to the fifth over 3n. Following all the super specific notation and conditions of calculus, this in its current state, you could argue, is not solvable. So we say, let f of x equal the natural log of x to the fifth over 3x, and then we're going to analyze the limit as x approaches infinity of the natural log of x to the fifth over 3x. And I already had a condition check up there and erased it. And I'm going to kind of do a sloppy little shortcut. This is in the form of infinity over infinity. I can't say that's equal to infinity over infinity because College Board is going to consider that a linking error and stop grading. But this expression, this new function passes that condition check for applying L'Hopital's rule. So applying L'Hopital's rule, we have the limit as x approaches infinity of, okay, let's bring that 5 down as a power. And bring that power 5 down using power rule and have 5 times the natural log of x. What's the derivative of natural log of x with respect to x? 1 over x. And what's the derivative of 3x with respect to x? Just 3. And if we let x go to infinity, what do we have? 5 divided by infinity is approaching 0 over 3, which means our limit is approaching 0. So thus we know, we're not hypothesizing it, we're actually doing a proper check. The limit as n approaches infinity of the natural log of n to the fifth over 3n is indeed actually equal to 0. And that is section 9.1. And again, we left a little bit of some formal notation and language, and we didn't talk about bounded sequences and monotonic increasing and decreasing, but at its core, that's what I need you to know in 9.1.